Hello everyone, my name is Elvis. So I currently work for Bacom Systems. So Bacom systems and embedded, there's no much overlapping there. So what am I doing here today? So basically for last couple of years, I was working as compiler engineer. So today I will actually share something that might be useful for you. And maybe you can actually like try something in your work, or just to actually see what people are doing in this space. So yeah, let me start. Okay, yeah, it works, it seems. Yeah, so before we actually go into writing our first LLVM pass, just one disclaimer. So this is actually related to LLVM, and we will not talk about GCC. GCC also has something similar, so you can actually write your plugins to do some similar work. But if we actually see how compilers are actually organized, so they have like three main components. So front-end, so-called middle end, and back-end. So in the, let's say, this middle end part, and a lot of things are actually done using so-called intermediate representation. But why is that? So basically, if we see here, so we have front end and we have Clang, Rust, Swift, Julia. I don't know, nowadays there's Mojo, there's Zig and other languages. So they actually transform their source code in intermediate representation, and then middle end can do a lot of different stuff, and then we can actually like have our target platform. So one example is, let's say that some optimizations that were written like 20 years ago, they are actually useful for languages that someone is creating today, or for example for us that was created, I'm not sure, like 10 years ago or something like that. So they can actually be used. So intermediate representation, LLVM IR, is actually like platform independent, and basically it's not related to source or actually the target. Okay, and in intermediate representation we have like couple of let's call them building blocks. So we have module that's like one-on-one relation with a compilation unit in C or C++. And then we have like functions, basic blocks, and instructions. So for today, we will actually this presentation. I forgot to mention this presentation will be actually code heavy. So so we will actually. I'm not sure if you can see. Okay, so we will base our example. Our pass on this example. So basically we have like simple C code here, and here we have like intermediate representation. So it's some kind of like a language, and this form is actually human readable form. You can mostly ignore it, but if you just see it's similar to assembly, actually people call that assembly, platform independent. So as you can see, if you focus on, let's say, add function with this add sign, you will actually see that there's like add instruction, that's fifth line. So there's add instruction, and then we just return the result. This is actually the main function in a control flow graph. We have 4 basic blocks. Basic block means like we have sequential instructions, and at the end of the basic block we have like a branch, and that's basically it. It's really important concept in LLVM. So what is an LLVM pass? It's a self-contained piece of code that can analyze or transform this LLVM IR. What does it mean? So basically, if it analyze, you can do some. Let's say that you have your code and that you want to estimate stack usage. You can actually analyze what you are doing and estimate and to see if you are above some threshold or not. You can actually do that. Transform, well, we can transform and do a lot of different things. So I'll share one example from, I think, 2 years ago. So when we say transform, it's basically like optimizations, right? So this is actually a lot of optimizations from O3 pipeline. So you can see, I don't know, maybe there's like 100 or even more passes, transformations actually. There's a lot of loop optimizations there. But you don't have to optimize it using like transform. You can do different things there. For example, in our case, we will actually we'll show that we can actually inject something. So let's continue. So how those systems are actually implemented. So if you already have your compiler or some other tools, so those compilers, those tools are actually already shipped to you. So you can actually use them, and then you have to plug in something to work. So basically, it's a simple mechanism. You just create like a shared object, and then that object will be DL opened, and then you find predefined function. You have like your object that it will return. It will call that and register something. And then you can actually use that. So in our case, we will actually, we can use this with opt. It works on LLVM IR, or for example, we will use Clang here. So if we wrote this plugin, for example, and our pass name is first, we will run it with opt like this. So when we compile, okay, when we compile our code, we can actually dump this LLVM IR, and the extension is LL. But we don't have to do it like that. We can just actually run it run with Clang, and we don't have to work on LLVM IR. We can work on any like C, C++, Objective-C, any other language, for example. So this is actually what you actually need to implement in your plugin. So basically, like predefined function is the name of the predefined function is at the second line, and then return type. So this is actually what you need to do. If we combine that and we just simply implement that and output something, if we run it with opt, basically it will write there that we register our pass, and then on top of that we can do a lot of different things. But what we can actually do here is an example that we will actually register one of our pass. So later on you will see that first pass that is on line 12, we are actually adding our pass. And this pass is actually function pass. So we have three different, let's say three different type of passes. So we can write pass on function, on whole module, and also like optimizations are so common on loops that there is a specific pass for loops. So we can do a lot of different things there. So this is our first implementation of first pass. So what we are actually doing, when we run clang or opt, we will just dump in compilation pipeline function name and number of parameters. And this will actually not transform our code. It will just like dump it. So we preserve all analysis here. So basically, if you are doing transformation, if you are doing something to your code, you have to say if you change that. So the other passes in the pipeline, should they also do something or not? Okay, so if we just run this, our example, if you remember, had add, sub function, and main. So basically, all of those functions had two parameters, so here we actually have that. But if we compile this, we will only, it will be the same. Like in the runtime, they will be the same. We didn't transform, we didn't do anything, right? So next pass, I mean, it's kind of similar. We are actually adding inject pass. But here, what we are doing, we are working on top of module. So previously, we run on all functions. Now we will actually do it on top of modules. And here we have a bit more code. So what is the general idea? What we want actually here to do? So for every module, this pass will be run. So what do we actually want to do? So we want for every function in that module to inject a function call. So basically printf here. I use printf here because it's similar. It's simple actually to show, but you can do a lot of different stuff, right? So here we will inject one instruction to for call for printf, but you can actually do a lot of different stuff. For example, there was another speaker previously sharing how they actually debug something. So they can actually just use debug message here. But they don't have to go into their code and to write something. They can just run this and into every function to actually add that that function was called. Why is this important? You will actually see later, but I can already share. For example, with C, you can kind of cover that, but with C++, there's a lot of functions that you don't know how they are created, right? So if there is like a constructor somewhere defined, you cannot easily find that function and to actually add a log line there, for example, if it's called or not. Okay, so what we are doing here, there's on line 4, there's our function prototype. So basically printf, it returns int, and it is variadic function, and there's a pointer to the format, right? So there's a format and then variadic parameters that we are actually doing. So maybe I can actually skip this part, but what we are doing, we are creating that function, right? So we are creating that function, and if you at line 11, that's our function, that's our printf function. So, and in the for loop, we will iterate iterate over all functions in that module, and we will do something. So the 3 dots, that is on our next slide. So what do we want to do here? So in this example, what we need to do is to create like format string. That's like a global string. That's one thing. Another one is, so that's on line 15. And then another one is function name. We also need a string for function name and number of parameters. And then on line 19, so what we are actually doing, we are injecting call. We are injecting call to that function, printf function. So, and then that's basically it. We will just return if we changed something or not. Okay, so if we run it, we will have this. Okay, and this is intermediate representation for add function before inject and after. So you will see that after this inject pass, at the second line, we have this call to printf. So if we run this on our program, so it will inject printf at the first line of every function. So if you don't like intermediate representation, here's some assembly. So basically add function on the left, and on the right, you can see like on line 15, we are actually calling printf, but before that we are preparing arguments for printf. If we run it, if you run this, so basically we are running this, and this is a runtime, right? So when main function was called, we just print, hey, main is called with argument size 2, and then add was called. Another one was if we give like some argument to our binary. Okay, so there is a difference if we are working actually on using opt or just like a clang, because clang is well defined. We cannot do that. We cannot inject our pass like everywhere. We need to do sorry. We have to like use predefined pipelines. For example, here we are actually using at early stage where it's actually safe to do that. And I also checked here if we want to run this pass only for optimization level 02. So you can actually do that as well. Okay, and I just wanted to share here like a simple C++ example, and this is not optimized, so you will actually see some scary things, because in a similar way, like in similar number of lines in C code, you had only 2 functions, but for this C++ code, because we are actually using IOStream, you will see some scary things, because this is actually number of functions that we have, and we injected in all of them, right? This is non-optimized code, and that's why you actually see that, because when you import that IOStream and when you create that object cout, basically it will create a lot of different objects and constructors that need to be constructed, and you will end up in a lot of different, like, I'm not sure, but there's like more than 100 functions that we will actually call in runtime. But if you have like optimized, it will be like around 6 or something like that. There's also important thing to note to say here. Printf is defined somewhere else, but here we are actually in libc. But here, what we are doing is we are using IOStream, and it will actually end up in our binary. That's why we have more functions here. So that's our pass. But what is actually possible with this infrastructure? What can we actually do with this, like, for example, pass manager, or we can do a lot of different stuff. We can do like profiling. We can write, like, for example, our profiling functions, I don't know, send data to Grafana and have defined declaration of that function that does that, and we can actually inject that. Other possibilities here, if you want to implement your own optimizations, you can actually do that. Or in the field where I worked, you can actually do obfuscation, different kind of obfuscations. So for example, if we go back and see add function here, it's so actually easy to figure out what this add instruction, what this add function does. But if we want to like change that for the, I don't know, some bad guys, not to figure out what it does, we can actually inject some code that is not that trivial to figure out. Or we can also like inject functions that will be run in runtime, like this printf, but to check some conditions, some environment where we run our, for example, if we not related to embedded systems, but if we don't want our binary to be debuggable, so we can actually inject checks. If someone is running debugger on top of this, then we can actually just, for example, choose to crash our application or something similar in that manner. So, for example, you probably used, who used sanitizers? None of you used sanitizers? Okay, so if you want to, for example, to detect if there is, who had the use after free error in their code? No one? That's weird. Okay, but if you want to detect that, you can actually, sanitizers are implemented in this manner. So basically, before or after functions, there some parts are actually added, and then there is a check to actually do to check if something happened or not. There's other possibilities that you can actually do to instrument, to profile your code. So, for example, in similar manner, you can actually like just add at the beginning of your function, at the end of your function, you can start a timer, end a timer, do benchmarking and similar stuff. And basically that's it. If you have any questions.
Thank you, Elvis. And now we can start with questions, if there are questions. Yeah, there is one question.
Oh, hello. One question. So, like, if I want to utilize it for, I know, tracing of the call stack, and if I use aggressive optimization, I mean, can aggressive optimization in the later stages of the Clang pipeline mess up with printf statements?
Yeah, not with printf statements, no, because I mean that's your code, right? Because this is not different than compiler generating like constructor for you. Basically, you are adding that. But compilers can actually remove code that you added, and then, for example, what I said for add function, if you add, let's say that you add like instruction add 3 on one of your variables, and then you actually remove that. Compiler can actually figure that out and optimize out that. So if you want like to do some obfuscation on top of that, like static obfuscation, what you need to do is use some tricks to actually like trick compiler not to optimize it, and then to have like that obfuscated function. For printf is not that easy, right? It's like it's like compiler generating constructor, but for other instructions it can happen. But even if you actually, let's say that you inject your printf in add, and later on compiler decides to actually inline that call into your other into main, it will still be there.